Okay, here's problem 6 from the October 2007 exam. And I'm doing this one because it's got 2 batteries in it. So it says, consider the circuit in the figure where all the resistors are 2 ohms. Calculate the power dissipated in each resistor. Okay, so the way to deal with multiple batteries is still just that you know that each battery causes voltage difference between either side of whatever the battery voltage is. So like for this circuit, we know that on this side of this battery, all the points connected to here are all at the same voltage, and we can call that one, let's just call that one ground, so we'll call that 0 volts here. Which means that on the other side of this battery, this point is at 50 volts. If we go through this resistor to this point, you don't know what this is anymore, so we'll call this some potential VA. And this side of this battery is also at VA. So the other side of this battery is at VA plus 20 volts. So the battery is going this way. So it's just adding 20 volts to whatever's on the one side of it. So there's 20 volts difference across this battery. So we know this is at 50 volts, some voltage VA, and this will be VA plus 20. And this one we know again is at ground. So now we know the voltages or have some relationships for every point. So now we can use the Kirchhoff's current law and write some more equations relating these voltages, and then we'll be able to solve for what the voltage is at A, and then we'll know the voltages at any point in the circuit. So we have some current going into this node here. So some current I, and that's going to split into 2 currents, I1 and I2, through these 2 branches of the circuit. And then at this node here, I1 and I2 will recombine again, and we'll get some current I going back that way. So we know that I is I1 plus I2. This is the Kirchhoff's current law applied at this node here. We also know that you can write some equations for the relationships between these voltages. So there's 50 volts minus VA dropped across this resistor here. So the V across this resistor is 50 minus VA is the current through that resistor, which is our current I, times the resistance, which is 2 ohms. So that's for this resistor here. Now for this resistor, we have just a voltage dropped of VA. So this is at VA, this other side's at 0. So VA is equal to the current through that resistor, which is I1, times 2 ohms. So this is, again, a 2 ohm resistor. And for this one, we have a voltage of VA plus 20 on this side and 0 or ground on this side. So VA plus 20 is equal to the current through here, which is just I2, times the resistance, which is again 2 ohms. Okay, so we have these 4 equations, and we have I1, I2, and VA as our 3 unknowns. So we're going to combine these equations to solve, we want to find the voltage at this point, so we'll find VA. So if we let's add these 2 bottom equations. So if we do that, we get 2VA plus 20 is equal to I1 plus I2 times 2 ohms. And I1 plus I2 is just I. So we get 2VA plus 20 is equal to I times 2 ohms. And now we can combine that with, let's see, this equation here, which also has I times 2 ohms on the right-hand side of it. So we want to combine now that with 50 volts minus VA is equal to I times 2 ohms. So we can set these 2 equal to each other. We get 2VA plus 20 is equal to 50 minus VA, or 3 VA is equal to 30 volts. So now we solve for VA. We get that VA is equal to 10 volts. So now that's the point here. So now we actually know the voltage dropped across any of these resistors. We have for this first resistor, we have 50 volts on one side, we have 10 volts on the other. I screwed that up. Okay, so let me start over with that. The voltage across this first resistor is 40 volts, which is equal to the current through it, I, times its resistance. We know that for this resistor, R2, the voltage across that was just VA. So we have 10 volts across R2, and that's the current through R2 times its resistance. And for R3, we have VA plus 20 volts at this point, so 30 volts and ground over here. So 30 volts across that resistor. But to find the power through each one, the power is the voltage squared divided by the resistance for each resistor. So the power through R1 is the voltage across R1 squared over the resistance. So this is 40 squared over 2, which is 800, and that's watts. For R2, we had 10 volts across R2, so that's 10 squared over 2, which is 50 watts. And R3, we had 30 volts, so the power is 30 squared over 2 ohms, so that is 450 watts. So these are the powers dissipated by each resistor. So the total power is 800 plus 50 plus 450, or 1300 watts total. So for part B here, it says show that the energy is conserved in the circuit by demonstrating that the power provided by the batteries is exactly equal to the power dissipated in the resistors. So we found by adding up the parts from the previous part that 1300 watts total dissipated. And so the power from the resistors, we found this, 1300 watts. The power from the batteries is the current through the batteries times the voltage across them. So the current through this first battery here was just I, which we found, let's see, we didn't calculate that yet. So we know that 40 volts is dropped across R1 because of I. So we have 40 volts across 2 ohms, so that I is 20 amps. So it's 20 amps going through this first battery. So for the first battery, we had 20 amps and a voltage of 50 volts. So that's 1,000 watts due to that first battery. The second battery, if we go back and look at the second battery, had a current of I2 through it, and so I2 caused a drop of 30 volts across this 2 ohm resistor. So you know that there's 15 watts. So 30 over 2, 15 amps through this resistor. So that's 15 amps through this battery at 20 volts. So that's 15 amps times 20 volts, which gives us 300 watts. So P total from the batteries is 1300 watts, which is what we expected. So the total power from the batteries is dissipated in the resistors.